Everybody hear me? Okay. So thank you all for coming. I am Diane and I'm a master's student with Peter Wilcock. So my thesis project is on river channel response to flow augmentation in the Diamond River in Utah. So how do we learn about how rivers work? So the best way to learn about, one of the best ways to learn about how rivers work is to examine channel response to their disturbance. So here I'm presenting a study that examines river response to nearly 90 years of flow augmentation. So the Diamond Fork had a very large and very long flow augmentation. And most of the studies that we have looked at are looking at an augmentation, which is a really big increase in discharge with a much lower magnitude, but a really long duration. And most of the floods that we've looked at are in a longer magnitude and a low duration. Diamond Fork is special in that unique, not special, in that it had a very large and very long flow augmentation. So my study area is the Diamond Fork, and it is southeast of Spanish Fork in Utah. This is a picture of the pipes and tunnels that are going through the Diamond Fork. So in 1915, Strawberry Tunnel, is this thing? Ooh, okay. Strawberry Tunnel was completed, which diverted water from the Strawberry Reservoir to the Wasatch Front. And then in 2004, the pipes and tunnels were completed and minimum flows were implemented in Diamond Fork. So water was diverted from the reservoir through Six Water Creek, which then flowing into Diamond Fork. So a bunch of sediment, all the sediment from Six Water was coming into Lower Diamond Fork. So there was a large increase in sediment supply by that time as well. So the diversion period was between 1915 and 2004. Then after 2004, the diversion period stopped and the water being diverted was no longer put through Lower Diamond Fork. So I'm specifically focusing on the Lower Diamond Fork is in this watershed. Okay. So the flow history of the Lower Diamond Fork is that the natural summer flows before 1915 were around, where should I stand? Were around 10 CFS. And then after the diversion period, they were around 100 CFS. So the typical diversion flows were around 300 CFS and the typical peak diversion was around 500. So there were, between a period of 1908 and 2022, there have been about 12 floods that were above 700 CFS. So that's about one every 10 years. So these floods were about less than 2 times the peak of the diversion flows. But 2 floods in particular in 1952 and 1984 were greater than 3 times the peak diversion flows. So this creates a process response model, and we need to understand what these punctuated disturbances did during the diversion period. So these floods were significantly bigger than the typical peak diversion, so we need to understand what their impact was for channel change during these diversion flows. So how does a channel change with increased flow? Channel response can be described on a more of a continuum scale in that changes in texture and aggradation, degradation, which would be raising and lowering of the bed, can be described more as a short-term response. And changes in planform, which is the pattern of the channel, and channel slope can be described as more of a long-term response. So if you increase the water discharge, this could fine or coarsen the bed. It could increase the channel width. It could increase or decrease the channel depth. It could increase the meander wavelength or the shift pattern from meandering to braided, or it could increase or decrease the channel slope. So what about the sediment? We can't really describe river channel change without talking about the impact of the sediment supply on the river as well. So that way we need to think about how sediment supply changes relative to the water supply. So how do we consider both water and sediment supply at the same time? Well, we can start by looking at Lane's balance, which provides an indication of this if if the channel is in a sediment surplus or deficit. But lanes balance is only the starting point for understanding river channel change, because we need to take into consideration the other conceptual models that will help us explain this channel's response. So this leads to my study design. So changes in water supply is more of a persistent channel change, while changes in sediment supply would be more considered a punctuated channel change. But I'm looking at changes of water and sediment supply to lead to a more punctuated channel change. So I'm going to be looking at local factors in the channel, and as well as valley slope, valley confinement, channel conditions, and hard points within the channel that don't allow it to change, such as road constrictions, or there was a levee built in 1984 that would be constricting the channel as well. So Jabari Jones was a previous master student on this project, and he examined geomorphic change throughout Sixth Water and the Lower Diamond Fork as part of a multidisciplinary study to evaluate future base flows. So for the Lower Diamond Fork, he noted there was general incision and widening in the channel. There was back and forth shifts between the widening area of the channel, and then the channel pattern was changing from single thread to braided. So he noted that the channel response depended on the valley confinement and slope, as well as the channel conditions and the vegetation establishment. So the more vegetation that was in the channel, the narrower it ended up being, is what he concluded. So in this chart above here, you can see that this channel has gotten significantly wider compared to the regional streams. And then this chart down below explains that and show that the channel has widened over a varied of time, but often reached a maximum point in 1952. And then after that, it started to narrow. So what I'm adding on to his research is I'm helping complete the story of the Diamond Fork. So what I'm going to do is develop details and describing the grain size and elevation of specific surfaces in the channel during specific points in time. So I am focusing on the 20th century, and that I'm going to look at specific locations that were in the channel, say in 1939, that were no longer in the channel in 2022. So I'm going to use additional air photos that I have found to further tell the story of what happened after the 1952 flood and before the 84 flood, and then after the 84 flood as well. So these are examples of what I'm calling abandoned surfaces to look at within the channel. So, and this image right here, you can see that there are 3 surfaces, 1, 2, 3, above the modern channel here. And this is the same image as here, but you can only see 2 in this picture. So I'm going to look at these surfaces and describe their bed size, grain size, and elevation to see if we can explain the story of what happened to what the channel looked like during these historic periods of time. And this is just another example of another study site, the Diamond Fork, and you can see 1, 2, 3, 4 surfaces here. And this site here is, well, the green area right here is this blue area right here. So this is just the preliminary mapping I have done of the abandoned surfaces in the Diamond Fork, in that this blue polygon here is an abandoned surface that was in the channel in 1939, but no longer in the channel anymore. And then this surface was in the channel in 1956, but is not in the channel anymore. So I can go to these sites and look and get their bed size and grain elevation, or bed. So, yeah, this is what these surfaces would look like on our LiDAR or 0.5 meter DEM, which Jabari was able to collect during his thesis, and this is what they would look like in space on a Google image. So my methodology is that I'm going to evaluate these surfaces for post-depositional modification. So I'm going to see if the bed degraded, if there was any road construction that prevented the channel from moving. And then for each of these surfaces, I'm going to compile channel bed texture, which I will be collecting in the field, looking at their elevation based on the LiDAR DEM, as well as looking at the channel width and pattern using the air photos that I have. And this will hopefully help me understand the channel's response to changes in water and sediment supply. And then this will lead me to evaluate conceptual models on explaining the channel response. So the imagery I have available starts in 1939 and goes up until 2016. The new images I have collected are in blue, and they are from 1964, 1965, 1971, and 1984. So those images will really help explain what happened post 52 flood and the 84 images I have are directly after the 84 flood. So they can really help explain what the channel looked like in 1984. The last part of my thesis would be evaluating these abandoned surfaces and explaining their elevation relative to the channel bed. So I want to understand their change in elevation. So yeah, okay. And then after that, I'm going to estimate the sediment delivery that happened through sixth water, as well as fill in the hydrologic time gap between 1918 and 1939 and 1970 and 1988 by creating a synthetic flood record that will, from gauges in the area, that will help me fill in the gap of the discharge information, that discharge information. So the Diamond Fork allows us to explore and evaluate river channel change due to flow augmentation. So the Diamond Fork is unique in that it experienced this long and large flow augmentation of over 90 years. So I want to investigate the patterns of channel change that will allow us to conclude how rivers respond to flow augmentation and large floods. Understanding how this channel responded to these two large floods will allow us to address the question of flood impact on recovery time in the presence of extensive channel change driven by this flow augmentation. Thank you. Any questions? Yeah. So how do I want to explain this? So the abandoned surfaces are surfaces that were in the channel at a historic period of time that were no longer in the channel. So I'm going to go to each of these surfaces and collect grain size data. You make a good point where yes, there could be some bias going on, which is something I'm still trying to figure out of how to make it not biased with, current channel conditions, because yeah, they have been reworked and stuff. So, but from what we understand of looking at these aerial air photos, that surface should have been was in the channel in that historical period, but it's not in the channel any longer. Yeah. Mm-hmm.
So it's possible that the 1984 flood wasn't augmented at all, right?
No. The version flood stopped in 2004. So it was augmented. It was augmented from 1915 to 2004.
I thought we figured out that they had turned off the transbasin diversions in 1983 and 1984.
I don't think so. I don't think so. From what I understanding, it's until 2004 is when the diversion flow stopped. But maybe my facts are wrong. But
I thought when we corresponded
we
decided that in 1983 and 1984, when the Great Salt Lake was full, they turned off the diversion. I was just going to ask whether it could be that the biggest flood that did the biggest shaping was at a time when they turned the diversions off. And it might, how that was going to complicate the story.
I'm not sure. Okay, yeah.
Sorry.
That's okay, no. Yes.
So back to the grain size thing, how different do you expect the grain size signal to be between these different historic channel blocks that you're now sampling kind of up in the abandoned floodplains and stuff? Do you think it's going to be a big enough difference that you'll be able to see it, or are there certain surfaces that you think are going to be finer versus certain channel beds that are finer versus coarser? Is that kind of the general idea?
One would hope. I'm not really, I don't have, I'm not sure what, I'm not really sure what they will look like, but I would hope that they're different so I can, compare them.
So again, looking at some of those pictures, and so how do you account for the fact that probably other land is changed to grazing, probably much bigger deal? You said things are getting narrower because of vegetation, wild vegetation wasn't there historically with grazing. So how do you think that's going to affect that? Not only are you changing augmented flow, but you're changing the rest of the land in that area as well.
So I'm gonna have to edit my mapping of abandoned surfaces to account for human impacts and the road, obviously. So yeah, I will have to take that into account when doing my analysis, because human modification has caused some of the surfaces to not be true abandoned surfaces anymore.